Hello everyone, I'm Insu from Georgia Tech. This talk is about how to find API misuse bug by comparing different multiple API usages. This is a joint work with Dr. Changwoo, Xujie, and Yeongjin Jang, and my advisor, Professor Taesoo and Professor Mayur Naik. APIs in today's software are plentiful yet complex. For example, in OpenSSL, there are about 4,000 APIs in version 1.0.2h. And APIs are really fast evolving from version 1.0.1t to version 1.0.2h. More than 100 APIs are newly introduced. And people use a lot of APIs when implement their software. For example, in OpenSSH, they use more than 100 OpenSSL APIs. This is not limited to OpenSSL, but browser like Firefox and the operating system like Windows. Complex APIs result in program mistakes. It is caused by the problems in documentation. Documentation is incomplete. For example, people mentioned that the documentation of hostname verification in OpenSSL is not detailed enough. And it is too long to read them all and understand them all. And there are some internal APIs which don't have any documentation. And more seriously, there is no automatic tool to support programmers. Most tools require some formal specification and precise semantics, but in reality, most of APIs are lack of them. The problem is that the programmer's mistakes can cause some security problems. For example, if we incorrectly use SSL library, then it may cause some man-in-the-middle attack. And if we incorrectly use API in Firefox, it can cause code execution, and in Windows, it can cause privilege escalation. To help programmers, there are three major ways: formal method, model checking, and symbolic execution. Formal method is a promising way, but it requires specification. But making specification is time-consuming, and most of APIs are lack of them. And second is model checking. Model checking also requires manual analysis to define model. And it is lack of semantic context. And symbolic execution, the problem is the scalability. These days, there were a lot of improvements on scalability of symbolic execution, but still it is hard to apply to large code. Except for these practices, there is a promising way finding bugs by using existing code. It is suggested paper bugs as deviant behavior in OSDI 2001. But it requires syntactic template like checking null or malloc. Juxta, which is introduced in SOSP 2015, it infers the correct semantics from the multiple implementations. But Juxta's approach is hard to apply beyond the file system. So our research goal is that, can we apply this method any kind of software without any manual effort? Our idea is that comparing API usages in various implementation. For example, if you want to find the OpenSSL API misuse, then first collect application which use OpenSSL APIs. For example, Cur, Nginx, Mmap, and Hexchat. Give them as an input to the API Sanitizer. API Sanitizer collects API context usage and resulted as majority uses and deviant uses. Majority uses are considered as likely collect, and deviant uses as likely bug. Our approach is really promising, and we have found 76 new bugs and in the large complex software, including Linux Kernel and Debian packages. But comparing different API usages is not trivial, because API uses are too different from implementation to implementation, and subtle semantics of the correct API uses, and handling large complex code is difficult. Here is an example of OpenSSL API. There is an API called SSL getVerifyResult, which uses the returning the result of peer certificate verification. At the first time, we might think the correct use is as follows: call SSL getVerifyResult and check whether it is OK. But it is not. If you read documentation carefully, it said if there is no peer certificate, then it always returns OK. So the correct use is that call SSL getVerifyResult and check whether it is OK. And also, you need to check whether call SSL getPeer certificate and check whether it is not null. This correct use is very subtle, so easy to make mistake. Here is a correct use of this API in Kernel. First, it calls SSL getPeer certificate and check whether it is non-null or not. If we follow the false path, then it checks whether it calls SSL getVerifyResult. And it checks whether it is OK or not. If we follow the true path, then actually this path is semantically same with the correct use. So it is correct use. There are another various implementations, including Nginx, mmap, and Hexchat. Similarly, in Nginx, there is a path that semantically same with the correct use. So it is correct use. And in mmap, it also has the path, so it is correct use. But in Hexchat, it calls SSL getVerifyResult and SSL getPeer certificate, but there is no return value check of SSL getPeer certificate. Therefore, it is incorrect use. Here is a question: can we distinguish between correct implementations and buggy implementations? There are some challenges. First challenge is the API uses are different from each other. For example, in Kernel, they use an equality check to check the return value of SSL getVerifyResult. And in Nginx and mmap, they use non-equality check. More complexly, in Hexchat, they use a switch case statement. So it is hard to find this bug by using just syntactic method. And the correct API uses have very subtle semantic. For example, in these 4 applications, they call 2 APIs, SSL getVerifyResult and SSL getPeer certificate. So, but the bug is come from the missing return value check in the Hexchat. So by simply just checking the absence of the API calls, you cannot find this bug. And handling large and complex software is difficult. For example, in these examples, the software are more than 100,000 lines of code. If you want to find the API misuse bug in Linux kernel, you need to handle more than 1 million lines of code. And the code is not simple as it is shown. Actually, the core code was simplified version. In real code, between the SSL getVerifyResult and SSL getPeer certificate, it contains many other API uses which make analysis harder. Here is an overview of API Sanitizer. From source code, we run relaxed symbolic execution and generate the symbolic execution database. Symbolic execution database contains 3 items: API calls, arguments, and constraints. From this symbolic execution database, we run 4 checkers: return value checker, argument checker, causality checker, and condition checker. This checker generates minority uses. Since minority is not always bug, we rank them to mitigate the false positives. First, I want to explain the relaxed symbolic execution and symbolic execution database. As you know, symbolic execution is not scalable because of the path explosion problem, and SMT is expensive because it is naturally the NP-complete problem. But to find the API context, we can relax symbolic execution by limiting inter-procedural analysis and removing backgatch and range-based. API sanitizer is focusing on finding how to use APIs, not how they are implemented. Therefore, we don't need to go into the API's implementation. Instead of it, we can see how they are used. So we can limit our analysis in intra-procedural level. An API context can be captured within loops. For example, malloc and free needs to be paired, but this property should be preserved regardless of loops. So we can remove backends to ignore loops. And since most of arguments and return values are integer, we can express most of API uses in range-based. Here is a symbolic constraint that the cert is non-null and error is OK. We can encode it as a range. For example, cert equal minus maximum to -1 and from 1 to maximum. Similarly, error can be encoded as a from OK to OK. Clang also uses this range-based symbolic execution in their compile time. By relaxing symbolic execution, we can handle large code base. Our symbolic execution is path-sensitive and context-sensitive. While doing the symbolic execution, we record symbolic abstractions, API calls, symbolic expression of arguments, and constraints. Here is a sample code, how we build a per-path symbolic abstraction from source code. First, in the source code, first it calls SSL get peer certificate. This call is recorded in symbolic abstraction. And it checks whether it is non-null or not. If we follow the false path, the constraint SSL get peer certificate is non-null is recorded in a symbolic abstraction. And it calls SSL get verify result. This call is also recorded in the symbolic abstractions and check whether it is OK or not. If we follow the true path, then SSL get verify result is OK is recorded in the symbolic abstractions. We generate such abstractions path by path. First path, we generate the symbolic abstraction number 1. And another path, we generate the symbolic abstraction number 2. And another path, we generate the symbolic abstraction number 3. By repeating this procedure, we can get multiple symbolic abstraction by paths. After getting the symbolic abstraction, we want to check them by using these 4 checkers. There are orthogonal and essential and security-related contexts, which are the return value and the arguments, causality, and condition. First context is return value. Return value is for the returning computation result or execution status. For example, if we call malloc, but if we miss to check the return value of malloc, then the null dereference can be happen. And in some cases, privilege escalation can be happen like in Windows. And the arguments is for inputs for calling APIs and their relationship. For example, printf-like function, the argument should be constant string. Otherwise, it can cause format string bug. And if you call malloc and mancopy, and these sizes should be well related, otherwise member corruption can be happen. And the causality means the causal relationship between APIs. For example, if you call lock but missing a lock, then it can cause deadlock. And if you call malloc but missing free, then it can cause memory leak vulnerability. And condition means implicit pre-post condition for calling APIs. Actually, the SSL get verify result and SSL get peer certificates is one of the examples. If we incorrectly use this API, then it can cause man-in-the-middle attack. As I said before, symbolic abstraction contains 3 items: APIs, arguments, and the constraints. We can extract the context from these symbolic abstractions. For example, return value from the constraints, argument from arguments, causality from API calls, condition from constraints, and the API calls. Due to time limit, I cannot explain them all. I want to show how condition context can be extracted from the symbolic abstractions. Here is a symbolic abstraction of call. We collect all constraints by event. Event can be any constraint or any call. In here, we pick event SSL get verify result is OK. And there is a constraint which is SSL get peer certificate is not null. And in Nginx, it also have the same event, SSL get verify result is OK, and the same constraint, SSL get peer certificate is not null. And similarly, in mmap, it also has the same event and the same constraint. But in Hackchat, it contains the same event, SSL get verify result is OK, but there is no constraint, so it is not added in a constraint row. By repeating this procedure, we can collect all constraints along with event. From this table, we can find what is majority uses. And from majority uses, we can find minority uses. Minority uses is simply the total event minus majority use, which contains a Hackchat. After getting this minority use, we should rank them to reduce the effect of false positives. False positives can be happen in majority analysis. For example, it is due to our lack of interprocedural analysis. In most of cases, it works well, but in some cases, for example, it call malloc and pass the return value of the other function, and inside the function, it can check return value. It is possible. And the correlation is not always causation. For example, fprintf can be repeatedly used when open is failed to print the debug message. But fprintf and open has no causal relationship. And there can be some correct minor uses. For example, in most of cases, people call string compare and check whether its return value is 0 to check the equality. But in some cases, the return value, the greater than 0 can be checked to check the ordering. So to mitigate the false positive, we use 3 standards. First standard is that more majority pattern repeat, then it is more bug likely. For example, if there is a 999 majority and 1 minority, it is much more bug likely than the 10 majority and 1 minority. This is because that it means we have the stronger belief of the correct use. And we can use some general information. For example, most of allocation function have the alloc in their function name, and it requires to check their return value. And we can use some domain-specific knowledge. For example, SSL APIs start with a string SSL. We can use such information for linking. Even though I explained the API sanitizer informally, our approach is formalized as a general framework. So I don't want to explain it in detail. If you are interested, you can find it in our paper. API sanitizer is written in 9,000 lines of code in total. Symbolic context generation is based on Clang 3.6. Compared with this framework, checkers are really simple. In total, it requires 1,000 lines of code of Python. For example, in return value checker, to implement it, you need less than the 200 lines of code. Through evaluation, I want to answer 3 questions. How effective is API sanitizer in finding new bugs? And how easy to use and how easy to extend? And how effective is API sanitizer's ranking system? API sanitizer is effective in finding new bugs. We have found 76 new bugs in large complex software, including Linux Kernel and OpenSSL. And these some bugs have the security implications. For example, there is a CVE Python chip imported heap overflow, which we can get a code execution in Google App Engine. And API Sanitizer is easy to use without any manual annotation. To generate symbolic context database, you can use your existing build command. And you can run checker, interrupt application, and inter application. And API Sanitizer's concept is really easy to extend. For example, if you want to check the integer overflow, then first you need to do is that finding what is the integer overflow sensitive function. Integer overflow sensitive API means APIs which have the security implications when integer overflow happens. For example, memory allocation functions. Integer overflow can be extracted from arguments and constraints. If arguments contains binary operators, and we can do and check whether integer overflow happened within given constraints. And collect all integer overflows and rank them. Ranking strategy is as follows. First, more integer overflows prevented by constraints, then we can know these APIs are more likely integer overflow sensitive. And we gave the higher rank to the incorrect constraints than the missing constraints, because missing constraints can be caused by our limited analysis. We have found 6 integer overflow by using less than 200 lines of code. API Sanitizer's ranking system is effective. This is the result of the Linux kernel with the return value checker. It generates 3,000 reports, and we have audited 400 reports and found 54 bugs. In the graph, the x-axis is reports sorted by the ranking. The left side is higher ranked one, and right side is low ranked one. And the y-axis is cumulative true positive bugs. In the higher ranked one, we can find 30 bugs in 20 APIs. And in the low ranked one, we found 24 bugs in 3 APIs. But there is a special APIs which have the 15 bugs in 1 API. Except for this special API, most of the bugs can be found in a higher ranked one. API Sanitizer is not perfect. It has many limitations. First, this approach is not sound and not complete. And it has a high false positive rate, more than 80%. And it is hard to frequently analyze. For Linux kernel to analyze it requires more than 12 hours. And we cannot fully resolve the path explosion, so our analysis can be stopped in functions which have the path explosion. I want to conclude this talk. API Sanitizer is an automatic way to find API misuse. It is effective. We have found 76 new bugs, and it is scalable. We have tested it in Linux kernel and Debian packages. API Sanitizer will be released as an open source, so please check our lab GitHub. Thank you.
Hi, William LeCoulter, APL. I was just interested in whether you could use APISan the other way to identify poorly designed APIs, like things that maybe have poor consensus on usage, or not compact ranges or other things.
Sorry, could you repeat it?
Could APISan be used to identify problematic or poorly designed APIs? So, like clearly what the example you showed in the OpenSSL library with having to do that two-stage comparison is is not an optimum approach for somebody, and somebody's more likely to make mistakes. So could you use APISan to help API developers write better APIs?
So you mean so apply the API sanitizer when generating API, so like a API specification, right?
Yeah, just using feedback to identify problematic APIs.
Yeah, yeah, it can be. Yeah, so I think API sanitizer can be used at that form. So actually, the most of the API vulnerability, as you can see in the OpenSSL library, it is due to their design is actually not well defined. So it is very subtle to use. I don't know why they divide that like APIs. So I think it can be used to notify how to design the APIs by the API sanitizer, I think.
Okay. Thanks.
Hi, Sumanjana from Columbia. So I have a question about your use of Clang. So the way you defined, the relaxed symbolic execution that you did. So the choices you talked about, it seems Clang is actually already making those choices. So did you make modifications to Clang's framework, or you did use it as is? Like the range-based constraints, lack of, rather limited interprocedural analysis, all those choices have been made by Clang, right? So have you modified Clang, or are you using Clang?
Actually, we saw the many bugs, the API misuse. We analyzed the API misuse bug, and most of bugs can be found in a relaxed form. So we choose to use them. So, and we compared our system with UC the under constraint, the symbolic execution presented in the last year. Actually, the under constraint symbolic execution takes the different direction against the symbolic API sanitizer. They do they also do the interprocedural analysis, and they also do the loop analysis and those kinds of things. But we run we run the two tools to the same code, and we have found some bugs. And I think it is not I don't think it is the perfect way to handle the symbolic, the path explosion. Actually, but it is working for just this context when you find the API context. So because of that characteristic that have the API context. So yeah.
Okay, thanks.
Hi, Jeremy Epstein, DARPA. The paper can sort of be summed up by the wisdom of the crowds when it comes to API usage. Most people get it right. Did you run across any examples where most people get it wrong, where most of the software you use when you actually dig into it, everyone is just doing it wrong, and so you're giving credit to the mistakes and blaming the people who use it right?
Actually, the most bug that we have found was actually the incorrect error handling, the return value check. So, for example, there is one API contains a string, a log or something like that, and people thought it is like it should be used as a malloc. So it checks whether it is null or not, but it is not. It returns a return code. It returns negative return code, so you should check the negative return code. So I think the most cases are the return value check. As the previous presentation said, the correctly handling error is not that easy. So I think that is the most cases.
Thank you.
Thank you.
Let's thank the speaker again.